Okay, today we are going to discuss about standing or stationary wave. So, standing or stationary wave. Okay, so what do you mean by standing or stationary wave? So, we have already discussed about superposition of waves. So, now here, if two waves are moving in opposite direction, for example, one wave is getting propagated in the right positive x direction or towards the right. Similarly, okay, this is the displacement time graph we showed. Similarly, another graph I can show you in which the wave is getting propagated in this direction, negative x-axis I showed you. Okay, so this is your time. Okay, this is okay moving in the left direction, and this is your displacement. Okay, so here I mean I consider the negative axis over here, or else you simply you can say one the direction of propagation of the wave is along this direction and the other wave is moving in the opposite direction this way, right? So in this case what will happen when these two waves, suppose I will write y1 and y2 will superpose with each other. Okay, will superpose with each other, they will result a standing wave or stationary wave. Right now we need to see what are the other parameters that also need to be considered. Okay, so suppose I will write y1 is equal to a1 sine omega 1 t in general. If you write a1 sine omega 1 t, right? And y2 is equal to a2 sine omega 2 t. So I wrote two equations, two different equations for both the waves, right? One is you can see y1 a1 sine 1 sine omega 1 t, y2 is equal to a2 sine omega 2 t, right? So here we are going to use some mathematical constraints to get this standing wave. So to get a standing or a stationary wave, proper standing and or stationary wave which looks like this way. Okay, one wave goes this way and the other wave comes back in opposite direction like this. Okay, like this. Okay, it's actually if you'll see the amplitude must be equal here to get a perfect standing or stationary wave. A1 must be equal to a2. Okay, the frequency omega 1 must be equal to omega 2. Okay, but the direction of propagation, as we said, okay, here must be different. So direction of propagation, if I will write it in general, direction of propagation, I will just as I said, omega 1 is equal to omega 2. Okay, I have to keep the time also the same, so t is also the same time. Okay, you are observing. So here if I want to introduce like direction factor, what we need to do? So here you can rewrite it like suppose I will write a1 y1 is equal to a, because amplitude is same, sine omega 1 is equal to omega. So let's take this as a and this as omega, which is same, right? And t, the time is same. Now in the forward direction and in the backward direction if you want to write. Okay, so here if you want to write this way, one is suppose minus kx. Okay, x being positive. Okay, and this minus k is the propagation vector. So this k actually is given by, what is k is equal to 2 pi by lambda, propagation constant or wave vector. What you said, 2 pi by lambda is actually what the corresponding value of phase, unit phase, right? 2 pi is the total phase and the corresponding distance is lambda. For a full cycle you can see this is your 2 pi which corresponds to lambda value, right? This is pi, this is pi. 2 pi corresponds to lambda. So 2 pi by lambda corresponds to unit phase, multiplied with what, the x, if x is the path difference, the distance covered, right? So we can write this way, a sine omega t minus kx, and the other equation y2 can be written as a sine omega t plus kx. So if you will write this way, you can see one is your minus X, you can see that indicates the direction in the distance traveled in the forward direction or backward direction. Here you can see this is plus x. So this equation indicates that one wave is moving in the positive x-axis, the other wave is moving in the negative x direction, right? So that way you can see. Okay, now if you want to find out the superposition of these two waves, so let me just write the final equation. So y1 is equal to a sine omega t minus kx. Okay, and the other one you can write y2 is equal to a sine omega t plus kx. Okay, so superposition means what? The resultant displacement, if I write as y is equal to y1 plus y2, then you just add these two, sine omega t minus kx, okay, plus sine omega t plus kx. Okay, so this is now two trigonometric functions, sine a minus b plus sine a plus b, that way. So you can open the sine a minus b and you can open the sine a plus b and see whatever you can common and just simplify it. So you will get the resultant wave equation. Okay, let me just share with you the equation only. Okay, it is not part of the syllabus. I just wanted to share it with you, just the mathematics behind. So you can write, if you will see here, uh, y1 is equal to a sine omega t minus kx, a sine omega t plus kx. Then we took a out and we wrote this way. You just open it like sine a minus b and sine a plus b. So finally you got this term 2a cos kx sine omega t here. So this 2a cos kx was taken to be the resultant amplitude, which is this, and then this sine omega t function. So it gives you a wave form oscillatory function as well, right? So so that is what we said is stationary wave. This is the form of the stationary wave or the standing wave in terms of mathematics. But here we don't need to derive any mathematical statement like this, but you need to understand actually what is stationary wave or a standing wave. So let me just share this one with you. 1 second. Okay, now here if you'll see two waves, you can see that the yellow one and the gray one, they are moving in opposite direction. The amplitude, the frequency, everything is same, but they are moving in opposite direction. One, the yellow one you can see is moving in this direction. The gray one is moving in this direction, opposite to it. So when they overlap with each other, they superpose with each other, you can see the pink. Okay, pink one is the resultant, right? And it seems as if it is flipping, right? All these, this moment the crest, there will be a trough. You can see that, right? So all these crests, alternative crest and troughs, they actually flip. Okay, they actually flip. So this is how a stationary wave looks like. Okay, so you can see that the superposition of two identical waves moving in opposite direction, they produces a stationary wave when they superpose with each other in a confined region in space. So confined region in space, this is the confined region in space we are considering, and in which these two waves are overlapping, and if you'll see the resultant wave, it looks like this. Okay, as if the crest and troughs are overlapping continuously, right? So any point you consider in one loop, okay, in one loop, when I said, suppose I will say this is the confined region in space, and two waves are superposing, identical waves are superposing with each other. So now you will see something like this. So one moment you got the crest, and the other moment it will flip to this side, same here, right? So any point you consider in this loop, they are together moving up and going down, right? So any point you consider, okay, in one loop, okay, will have same phase because they are moving in the same direction every time, right? And any suppose I will consider one more point, okay, here in this loop, this is one point, and you take this another loop, adjacent loop, then you will see when this one goes up, you can see it from the pink wave, resultant wave. So when this one is up, the other one is exactly opposite, you can see. So there can be a phase difference of 0 or pi, okay, in a standing wave or a stationary wave. So when you will get 0, if you are considering 2 points in the same loop, okay, then 2 points in same loop, 2 points in the same loop will have 0 phase difference, and pi phase difference when 2 points in the adjacent loops. Okay, one point in one loop, the other point in the next loop, right? Then there will be a phase difference of 0, phase difference of pi. And when 2 points are in the same loop, you will the points will have a 0 phase difference. This is the basic, or the major difference between a progressive wave and a standing or stationary wave. In a progressive wave, if you will consider any 2 point, there will be a phase difference that will range from 0 to pi, 0 to 2 pi, right? You can have any low, like here or here, so there is a phase difference, right? And that phase difference we have already, like, we can find out what is the phase difference just by finding out what your del theta is del omega by del t. So del theta is sorry, del omega is equal to del theta by del t, or omega is equal to, let me just write this way, omega is equal to del theta by del t. So your phase difference del theta can be determined from omega del t. So this we have already done. So any point you consider, if there is a time difference between these 2 points, because this is our time axis and this is our displacement xt, right? So if there is a time difference, then definitely there will be a phase difference del theta, and that varies from 0 to 2 pi, because 2 pi is the periodicity we said here, right? But in case of a standing or a stationary wave, it is not, there is no range like 0 to 2 pi. 2 points, if it is in the same loop, will have a phase difference 0, because both the points are moving up in the same time. And pi, if these 2 points are in two adjacent loops, two different loops, okay, adjacent and different loops, then it will have like a phase difference of pi. Okay, so this is what is important. So this is how the superposition of two identical waves moving in opposite direction looks like. Okay, so let us see one simulation. Just wait for a second, it is loading. Okay, now in this simulation, what you can see is overall, like, it's written manual oscillate pulse, fixed end, loose end, no end. Now here, two ends are fixed here. You can see both the ends are fixed here. This is the end which is fixed. This is another end where you have clamped the beads, you can see, right? And then let us see what are the other options given in this simulation. Okay, you can see damping. Okay, if you can adjust the damping. Okay, so damping means what? You can adjust the coefficient of damp, or damping coefficient, right? And then you can see the tension here through the string. Here you can make it low, moderate, and high. All other options like rulers, timer, reference line, and all, right? So slow motion or normal, these are all given. Right now, what you can do is you can move this one up and down, right? This part, this end, you can move up and down. You can see these arrows, right? So if you do it, I just adjusted it to no damping at all, right? And then fixed end. Then if I'll do this, if I'll make some movement over here, then you will be able to create a wave pulse or disturbance which will move through this string and will reach to this point. And this point we said is fixed. So if a crest is reaching to this point here, then it will give a upward thrust, but as the point is fixed, it will give it a downward thrust. So what will happen? Whatever, I mean, if a crest reaches here, then it will create a trough, right? If a trough reaches here, then it will create a crest. That is what we have already done in the reflection of wave, because the two ends are fixed. So we can say like reflection from the rigid, or you can say denser medium, right? It will introduce a phase of pi, right? So if I'll just move it up and down like this, you can see, suppose, see exactly the opposite one is coming, right? So it depends upon what kind of pulse you are actually creating, right? So depending on that, you will get back. Okay, so this is how it goes, right? Let us do this way, like, further you can see the superposition, you can see easily, right? So let me just reset it, and again like this, you can see, right? If there is a damping value, you can see gradually the oscillation damps this way, none, and then I will do this, you can see comes back, it goes, and then if I'll keep on continuously, continuously I will give the disturbance so that they will superpose with each other. Then let us do like this continuously, you can see if I'll do this, okay, and keep it at no damping, and then this just do the same thing, like continuously you oscillate it, okay, continuously you oscillate it. So the waves, okay, that will oscillate, I mean, the incident wave and the reflected wave will keep on oscillating, and indefinitely with respect to time in that confined region, you will be able to see that there is, a continuous pattern, a particular pattern that you will be able to see, right? Indefinitely with respect to time, because we said there is no damping. Now at this point, if I will increase the damping, then what will happen, you see, okay, now you can see it's settling down because the amplitude of vibration will be affected, right? So this way you can, okay, manual, or I'll do this way, you can see, if I do the oscillation this way, you can see how the, see the, just see the crest and trough, alternating crest and trough, the moment, I mean, initially it was a crest, okay, a peak, can be a trough now, right? So this is how it looks. You can adjust the amplitude here, you can see, you can increase the amplitude here, right, and see the pattern, and then you increase the frequency, keep on increasing the frequency, you can see how it looks like, right? Okay, so this way you can do. And if I'll make it a loose end, and we'll do the same for the loose end or a rarer medium, we had already discussed this, a frictionless, a ring structure can be considered here, so there is no friction, then you can see how the oscillation looks like. And no end here, okay, almost the same, loose end and no end, okay, fine. So this is how it looks like. Mathematically, we said it is simple. It is just, give me a second. So mathematically, we just said it is nothing but the combination of these two waves. Okay, these two wave functions, you can see, I mean, the wave equations to give you final oscillatory wave function, but it is different than that of the progressive or the traveling wave. Okay, so this is how a stationary wave and stationary wave, the difference between a stationary wave and the traveling wave. So the first thing you need to keep in mind is the phase difference, okay, has a value between 2 points that ranges from 0 to 2 pi in a traveling wave or a progressive wave. But here, if you are considering 2 points in the same loop, they will have zero phase difference. If you are considering the 2 points at two different loops, like, adjacent loops, then you will have a pi phase difference. So now if you can just see what we said, stationary wave can be produced by both transverse and longitudinal wave. In stationary wave, particles vibrate with different amplitude. Okay, particle vibrate with different amplitude that we saw actually here. You can see they vibrate at different amplitude. One point, if you'll see, the amplitude of vibration is maximum. At certain points like these points, if you'll see, there is no vibration at all. The particle which is here has no vibration, whereas the particle which are here, okay, having maximum amplitude of oscillation, right? Okay, or vibration. So that is what is one point. So the point where amplitude becomes zero, the amplitude becomes zero, where we said these are the points, right? These are the points where amplitude becomes zero. Okay, we called those as node. And the point where amplitude becomes maximum, we call those antinode. Okay, so these are the characteristics. Then as the position of nodes and antinodes does not change with time, the wave is called stationary or standing wave. So the position of the nodes and antinodes doesn't change with time. The wave is called stationary or standing wave. Or in other words, you can say as the energy or energy or momentum transfer is confined in a certain region in space, we call this stationary or standing wave, right? Okay, so once this is done, we can talk about harmonics in the next class. So I'll show you, like like here we discussed in that here we discussed about different, you can see fixed end, what will happen, loose end, what will happen, right? So we will consider, like different situations where we will consider two confined region fixed end and one fixed and one loose end. Then we will see how the frequency variation actually occurs, right? How the frequency, different types of frequency we can obtain, right? So that the quality of sound, or the final wave, we can actually see, okay, what will happen to that particular sound or that particular wave, right? So in the next class we will continue.